let's start. Okay, I'm going to spend a lot of time over test 3 just to show you what is the kind of thing you need to be prepared for, because final is coming soon, you know, December 15th, which is what, less than 3 weeks, or maybe it's 3 weeks away. And I know it's been tough for many people because I don't know the class average, because it's now in the grader's hands, and I don't know where's the grader. Somewhere out in space, maybe going to Alpha Centauri, I don't know. We'll have to see. But I'm spending time over the test 3 in order to help you prepare for the final, which would be double, because instead of an hour and 15 minutes, it's 2 hours and 15 minutes. So I need to sort of help you prepare, because I want you all to, in fact, you may not have done well, but you want to improve so much better that you make up for your not as ideal performance relative to the class average. And so I'm now going to go over the test 3 questions, all right? So the first one is, in a way, very simple. It just says, I have 2 identical light waves, A and B, emitted from different sources and meet at a point P, somewhere further down the turnpike. The distance from source of A to the point P is LA. All right, that's easy. Oh, can you see the screen? You cannot see the screen? Yeah, okay, everybody can see the screen. If you cannot see the screen, I cannot help you. Those are all technical difficulties having to do with your own browser. So, but okay, so there is a beam from source A to the point P, whose distance is now L sub A. And then source B is at a distance LB from the same point P, because we're interested in what is happening at P coming from 2 sources. Now, then this question has a sort of a list of statements. And when you deal with choice, with these kind of choice questions, you have to read all the statements in the context of the problem and then decide, okay, which statement is necessarily true. Sometimes these choice questions will give you 5 statements and then say which one is necessarily false. In other words, all the others are okay in the sense that it is not against whatever principle. But here, this one says is necessarily true. It must be true concerning the interference of the 2 waves. And what we mean by interference, I have 2 light sources. Somehow at point P, it is dark. I have 2 light sources. Somehow at point P, it's dark. That means there is destructive interference. Okay, so then we go through the statements. It says A and B will interfere constructively because the amplitudes are the same. Now, is that correct? Cannot be. Because if it's constructive, what would that point P be? I need your help. If it's constructive, the point P, would it be dark or bright? It would be bright. So if it is constructively will interfere, means that they will destructively. When you say you interfere, you are basically, I expected light and now there's no light, you have interfered. So when they say will interfere constructively, it is saying things that are opposite. So it's not true. And then the second statement is, they will interfere constructively if LA equal to LB. Now that is true, because the path from A to P is the same as the path from B to P, And since it was identical light wave, namely it has the same wavelength, then they will interfere constructively. So this statement is true. And then this other one says, oh, it will interfere destructively if they differ by m lambda, where m is 0, 1, 2, or 3. Now that cannot be true, because if they were different only by integral multiple of a wavelength, they will be constructively interfering. So this one is not true. And they will interfere destructively if LA is not equal to LB. That's not true, because LA and LB, they could indeed be not fully interfering. So, and A and B will interfere constructively because their wavelengths are the same. Again, it has to be, if their wavelengths are the same, A and B, but there's no statement about what is LA versus LB. So this is not necessarily true. Are you following the logic? I'm reading each one and I'm trying to say, is this necessarily true? Well, they will interfere constructively because their wavelength is the same, but you didn't tell me what is LA, what is LB. So therefore, this is not necessarily true. This one is necessarily true, okay? I just want to sort of help you. When you read these multiple choice on whatever these tests are, just be careful to read it carefully, okay? All right, so this one is easy, but just to help you train your alertness. Okay, then the next, which one of the following statements best explains the interference patterns? Which one of the following statements best explains why interference are not usually observed for light from two ordinary light bulbs? Like I have light from my ceiling light, and then from my table light. Why is it that they don't interfere? Well, it gives you 5 statements. Diffraction effects predominate. It's not going through any slit, so that's irrelevant. The two sources are out of phase. Well, we don't quite know that. But the two sources are not coherent. Now that is very true, because the light that comes from the desktop lamp, it is due to the buzzing around of the wire, the heat coming off, and it gives off light. Whereas the LED light up there in the ceiling, it is not coherent. It's not in sync with the desktop. Therefore, this is the statement that is best explained. Interference patterns is too small to observe. Well, is not the best explanation of why they are not interfering. And then light for ordinary light bulb is not polarized. Well, that is irrelevant because I don't have Polaroid glasses on. So out of these 5 statements, this is the one. It's very easy if you've already understood the coherence in interference. Okay, so now the third one. You say, I have a Young's double slit experiment with 2 slits and green light. And they even wrote down for you, red light 620 nanometers, green light 495, and blue light, meaning that red light is longer wavelength than green light and blue light is shorter wavelength. All right, so they are preparing you for it. And they say green light is incident on the 2 slits. The interference pattern is observed on the screen up there. I only show you this bright one. Which one of the following changes cause the fringes to be more closely spaced? Or in fact, I actually do give you. Oh no, the blackboard does not, but I uploaded from the lecture notes, right? That you can indeed have bright fringe, dark fringe, and another bright fringe, and so on. You can have bright, dark, bright, dark, bright, dark, right? And so now they say, which of the following statements is correct? If you use red light instead of green light, would they become closer together? That's the question, right? Which one of the following changes would cause the fringes to be more closely spaced? You say, why don't I try red light? But they already gave you a hint. Red light is longer wavelength. If it is longer wavelength, do you remember the formula for the interference? Is sine theta equal to, for constructive interference, it's m lambda over d. So if your lambda is longer, it actually would be further away. You're not squeezing the fringes, you are spreading the fringes out. All right? So this is not relevant or cannot be the correct answer. Or move the screen further away from the double slit. Well, if you move the screen further away from the double slit, are they going to be closer together? Now I need your help. I'm in a very tense situation. I'm trying to take a test. I need somebody to help me. No, they will be further apart. Why? It's like having a movie projector. Your screen is further away. Oh, the image is now even bigger. So this is not going to help to move the screen further away. But if you move the screen closer together, you didn't change the wavelength. It's still green wavelength, but you now move it closer together. Then, of course, the fringes will now come closer together. Move the light source further away from the double slit. You move your light source further away, it only lowers the intensity. You're not changing the fringes. You're only changing the intensity of what you see on the screen. So this does not help either. So only this answer is correct. Are you following now? I mean, it does require a lot of thinking. You have to read it carefully and then think. Read it carefully and then think. All right? Okay. Now, number 4. Now, this needs a little bit more grasp, right? You have a soap bubble, a portion. It appears yellow when viewed. When you have white light, that means it is filled with yellow, red, blue, green, violet, and so on, orange. So it is filled with light of various wavelengths, and they will be reflected off this film. And this film is on top of water. So we call this index of refraction little n, and this index of refraction capital N. All right. And then we already learned in our class that there is this effect that when light wave number 1 is reflected off a medium whose index of refraction is bigger, that there is a 180-degree phase change in light wave 1. But light wave, when it goes through here and is reflected off a medium whose index of refraction is less than it, because this n is greater than capital N, then there is no 180-degree phase change. So there is this extra little twist, if you like, extra little twist that causes a 180-degree phase change. And now we have to be careful for the interference between light wave 1 and light wave 2. Okay? And now when they say that that there is a yellow hue, it can be, and this question is just saying, supposing the reason why it can be a yellow hue is because there is constructive interference for yellow. For yellow wave, for the wave, for the light of yellow wavelength, that there is a constructive interference, that then there appears to be more yellow than green, blue, red, and so on. Then question is, what is this thickness that causes just this effect? Well, you have to now look up your notes. And you remember the notes are for constructive interference. Oh, there is this extra half wavelength, right? Because 2T, this is the thickness of the film. The wave actually, this second wave, wave 2, had to travel extra distance 2T. But when it came out, it found that its brother, well, not its brother, but its cousin or whoever, the one that was part of the original wave, wave 1, now is 180 degrees out of phase. That's why now there is a added 1/2 wavelength. This wave 2 says I actually only travel extra 2T. So it is whatever is my wavelength. But now you, my cousin or my friend, wave 1, or you now are an extra half a wavelength away, twisted. So then there would be if I have m plus a half, namely my travel length is not exactly m lambda, but m plus a half lambda, then when I come out, I match up with your half lambda so that we now are constructive interference. Are you following my logic here? It's from here that I want to know what is the condition for constructive interference. And then I now say that I actually travel, and I will travel 2T, twice the thickness, and in so doing, my path length was actually m plus a half lambda. And if you did not change your phase, there would have been destructive interference. But because I came out carrying now a phase, which is m plus a half lambda, it exactly matches with your 1/2 lambda phase change. So then we are constructively together in sync. So we will have constructive interference. Is that clear? I mean, we already did that in our class, but for an exam like this, you then have to say, gee, I go look back all of my notes, but then I better not look up the wrong formula, right? And here it says that there was constructive. I should have underlined it, but anyway, on the blackboard, it will not underline it for you. Or maybe next time I give a question, I should underline it to hammer it home in your head because you are so tense, right? That there is constructive interference. So the condition is this. And therefore, whereas since I downloaded also the other case. If there were destructive, it would have been that I actually went twice the thickness and my path length was integral multiple of the wavelength. So then when I came out, I am 180 degrees out of phase with you because you had this funny twist in your reflection of a denser medium. And so we would then be destructively interfering. But in here, what we need is constructive interference, and constructive interference would be then 2T is 1/2. You see, it becomes 1/4. But now, I didn't download this, but you have to remember that the wavelength of light, when it is going through a medium, that the wavelength is now shorter. The wavelength is now shorter because the velocity of wave is now slower. The frequency remains the same. It is still jigu, 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 the same frequency, but now the wave velocity in a medium is slower, therefore the wavelength is now smaller, and therefore it is lambda over n, where n is the refractive index of this medium. So this answer really came from here, plus the fact that this should be the wavelength in that film, and the wavelength in that film is lambda over the index of refraction. Is that okay? So what I'm trying to teach you is the question does not say, hey, you should remember this involves the wavelength of the light in a film. This involves constructive interference, destructive interference, and so on. You have to then search through your lecture notes, but then always remember that here is the wavelength propagating inside this film. Therefore, it should be the wavelength of the light inside the medium, whereas these guys, their wavelength continue to be lambda. Their frequency is still the same as our frequency, but its wavelength is lambda. But here, for this equation, when you use this equation over here, when you use this equation, you have to remind yourself that it is lambda over the index of refraction, little n. Okay? Okay. And now the other warning, I'm sort of like, if I had been, let's say, kinder, more of a compassionate, let's say, exam giver, how come I use little n for this guy and use capital N for that guy? You see, little n is bigger, right? Little n is 1.40, capital N is 1.33. Why didn't you use, Professor? Why didn't you use this capital N here and little n there so that I can understand it? Well, this nasty professor just wanted to make life more difficult for you, I guess. And then just simply use, right, and simply use little n for 1.4 and capital N for 1.33. So as to confuse you, all right, because that's what a multiple answer is, to confuse you. But you have to be firm enough to now say, I know it is lambda over the index of refraction. And then according to this figure, you, Professor, have called this little n. Therefore, it should be lambda over little n. Okay? All right? I'm trying to help you so that you can do much better in the next test, which happens to be the final. Yes. Oh, you mean whether this question will appear in the final? I'm not saying that this question will appear in the final, but things that are related to in thin film interference, air wedge, and those kind of applications, there will be some. I won't know because I haven't yet made the final. Okay, so let's go on. Now, number 5. Oh, this is a multiple answer question. In the Young's double slit experiment, green light is incident on 2 slits. Well, you know which is the Young's experiment is the double slit experiment. Interference pattern is observed on the screen. Which, oh, we did this one already? What did I do? Oh, I see. We did this one already, right? Okay, then go over. This one. Light of wavelength lambda nanometer is used in Young's experiment with slits separated by d millimeter. And here again, just a warning. There's always these little units. This is nanometer, 10 to the minus 9 meters, and this is millimeter, and you have to be careful when you use the equation that you have already included the fact that this is in nanometer, this is in millimeter, but the equations all have to be in the same meter unit, and so you have to have conversion factors. The screen is located at a distance L meters away from the slits. Now they want to know what is the distance on the screen, because your screen is 5 feet away, 3 feet away, 6 feet away, and now they want to know what is the distance between the bright fringe from the central fringe, right? So they say, find the distance on the screen between the central bright fringe and the first order bright fringe, and recall or remember that for small angles, sine theta is approximately the same as theta, so long as it is in radians, right? It would not be this if this is in degrees, and you say this is sine 30 degrees, that's not 30 here. It is only when theta is in radians. And they want you to give the answer to 3 decimal places, and then this little comment here that this random block will include multi-answer and calculator form questions on dark fringe. I don't know whether these blue comments help you when you are doing your test. Do you people find it helpful to have these little blue comments to let you prepare, since it is randomized block? Does it help? Yeah, I mean, sometimes I don't know whether it helps, but certainly it would help, because you would know that if I'm doing this before the multiple answer comes up, I already need to work out the set of formulas, and I will keep that set of formulas when the multiple answer come up. Or the other way around, when the multiple answer, I already know which is the correct formula. I keep it and anticipate and know that there will be another question involving the same thing with a question of numbers, putting numbers. All right, so now for this one, we remember this formula. It's bright fringe, so we remember this formula, right? And we also know what was theta, what was lambda, what was d. And here's the, well, one of the text lecture notes example. But this d is not necessarily this d in terms of numbers, but this is an example. You have the central fringe, and then you have now the first order bright fringe, right? And you now want to know what is the formula to use. Well, you know what to do. Then you just say m equal to 1, because that's the first. This example is m equal to 3, but this was from a different context. But this question says it's the first order bright fringe. First order is what? M equal to 1. Are you okay with this? I'm sort of like I'm you in the exam, and then I'm all, frustrated, and I go into my lecture notes and I say, oh, there's this, and this one says m equal to 3, so I put m equal to 3, and then Blackboard will say you are wrong, right? Because this picture, yeah, if it is second order, but they specifically ask for first order, namely the next bright fringe. Okay, so you use therefore this y, namely for m equal to 1, and then you know the angle theta, and then this is trigonometry. The trigonometry then says it's L tangent, because you know the angle. Trigonometry tells you that. All right? Any issues with this? Okay. All right. So now, let's go on. Is this number 6 now? And here now, this says that light, it is now again, the same situation. You have wavelength light incident on the double slit, and the double slit has the D. Incidentally, whatever is the dimension D, blackboard may give you totally randomized numbers. Whatever's the wavelength and whatever's the D, right? But we now say that the screen is located at the distance L, but now what they want is the different. They want dark fringe. When we did it in the class, I don't remember, did we do dark fringe or did we do bright fringe? I think we did bright fringe, but it's no big deal. We did bright fringe, but now I think on blackboard it also had a color here to emphasize that on the blackboard. I think it should show that the question is not bright but dark. So the light bulb should come onto your mind somewhere and says, "Oh, be careful! It's not the same formula that we now have to add a 1/2, right? That we now have to add a 1/2 because we want interference. We want it to be 180 degrees out of phase." Okay, so we now go and say, okay, I now want dark fringe. And somewhere in the lecture note, there's a picture like this. And we then say, oh, what the reason why it is dark is that the path length from this S1 slit and the path length from S2 slit differs by half integral wavelength. And so you now say, whoops, therefore it differs from the previous one by now having lambda over 2. Did you follow? I mean, if you go back to the previous one, it was m lambda over d, but now it is m plus a half lambda over d for destructive interference, for it to be dark. And that's why instead of lambda over d, it is now lambda over 2d times 10 to the 6. You see where the factor of a half comes in? For first order. All right? Okay. So, somebody had a question? All right. So now, oh, this is one where we're doing the multiple choice. And, oh, this is dark. So actually, this question is sort of like what was the previous question. Previous question, you had to calculate. But this question, you have to figure out the formula. And we have already learned that it should be lambda over 2. It is not 3 lambda over 2. That would be not the first order bright. It is then the next bright. Not the first order dark. It's the next dark. And the next dark has to be 3 lambda. It cannot be 2 lambda because 2 lambda would be bright fringe. So it is 3. If the question asks for the, I think they call it the second order bright fringe, or do they call it the third order dark fringe? I'm not in that language, in that field. So, but if you want the next dark fringe, then you would use 3. But they ask for the lowest order dark fringe, so you should use lambda. All right. Okay, let's go on. Oh, somebody has wait, somebody had a question. Come, ask. Can we go back? Yeah, which one? Here? Is it this one? Yeah, okay. What's the question? I mean, let me say it again. This one and this one both result in dark fringe. Lambda over 2, 3 lambda over 2, both result in dark fringe, but this one occurs at a bigger angle. So it is not the first dark fringe, it is, as a layman would say, the second dark fringe. But they may call it the third order dark fringe. Those technical experts. I'm not one of the technical experts, but for me, it would be the first dark fringe and then the second dark fringe. The second dark fringe, you don't use 2, you use 3. Okay?
Professor,
Yeah?
can you hear me?
Yes?
Okay. So for the first bright fringe, what would that be then?
Oh, we had the first bright fringe. What? We had that before. M equal to 1.
And first dark fringe is m equal to.
It's m plus a half, so it's, yeah, you have
Oh,
it.
okay, I get it.
Yeah, you got it now? Yeah. I mean, you just have to sort of start with this and then say, this is where it is the bright fringe, where they were totally in sync with one another. But when you now need to be dark, you want there to be interference. So they call this m equal to 3 bright fringe, which is third order. But for the dark, it should be now m plus a half. And this is where it is m plus a half, where m, namely m is equal to 0, so it's plus a half, right? Okay. Okay. All right. So now let's get to here where there can be a lot of confusion, and yet it is Einstein's special relativity, which is interesting in itself. And this one says, in the year 2100, I guess not yet, we are only 2021, so another whatever, so many years. In the 22nd century, we are in the 21st century, an astronaut wears an antique but accurate quartz wristwatch. It's like a special cesium atomic clock, but this particular question says, "Ooh, I have a very fancy Rolex watch, right? Quartz wristwatch on a journey at a speed of so many meters per second. You know, it must be like not quite the speed of light, but maybe, you know, 2.5 times 10 to the 8 meters per second. The speed of light is 3. Oh, I think in Blackboard, this correctly puts it as 10 to the 8th, right? It was not 108. It's in my copying and pasting onto the slide down here. I did not, I better remember to correct it when I upload all right. It's 10 to the 8th meter per second. According to mission control in Houston, the trip lasts so many hours. Man, it lasted, let's say 10 hours, 12 hours, whatever. How long was the trip in hours as measured by the astronaut on his watch? So now we have to we have to sit back and say, what is this professor asking? What is he asking? Is he asking for time dilation? Because I sort of vaguely remember in the lecture notes for special relativity, one of the big items is time dilation, and this does involve something about time, right? So you say, I look it up. Oh, yes, time dilation. Bingo, I have this formula. You can look it up in the lecture notes. But now you got to be careful. What does this and what does this imply? What does this imply? which time are they for this formula to apply, to use this formula? What is this? Is this the improper time, proper time, forgotten time, ancient time? It's the proper time, right? Now, which symbol does it refer to? We say, yes, this should be proper time, but does it refer to this or does it refer to this? Oh, my friend, somebody had a choice already. What was it? You see, this question, the crucial issue for this question is, which time is the proper time? Is it this time or this time?
Capital T.
The capital T. Thank you. You got it. It has to be this one because that's the guy who is now measuring it. He wants to know how long does it take to go to Alpha Centauri. So he is measuring it, right? And his watch is with him. So this clock or this time is what his watch tells him. You know, it is 12 p.m. according to his watch, and then he arrived at in 2 p.m., right? So then he says, that's my proper time. Then this guy, oh no. So you therefore use this as the capital T, and then this delta T is this little t. I thought I put some arrows here, but maybe I didn't. So that this formula then says that I should use this, right? I should use this because this is now the actual proper time. And this is what you, mission control in Houston says, oh, it was, 15 hours. But the astronaut says, gee, it didn't take 15 hours. According to my watch, it only took 2 hours or whatever. All right, so this then is a good way of saying, I know what's involved is time dilation. The only thing I have to be careful is which is proper, which is improper. All right. So this was easy, right? Any questions? Okay, so now let's go on. What, somebody had? Yeah, no question. Okay. So now we go to the same question, but now calculated. Remember there was this formula before, and this random block will also include the numerical calculation of the length of the trip. So just to prepare, well, here, now this is one where they want to know how long was the trip as measured. So we already know it should be the time dilation, and that's the formula. And what we have to now say is how long was the trip as measured by the astronaut. And so we say this is the proper time. And they want to now know how long. Well, that is therefore whatever mission control says. Mission control says it took 14 hours or 12 hours. Then it should be whatever the mission control says times square root of 1 minus v squared over c squared. But you notice the formula you should use is 1 minus v squared. Why? Because this is in units of c. So if v is already in units of c, c cancels out. So it's just 1 minus v squared. All right? So this is, again, you got the concept. It involves time dilation. You have the formula, but it takes discernment. It takes a little bit of, you have to be alert. If you came to the test and you were already groggy, then it will be very easy to mix these up. But if you are alert and then you say, oh, I know the astronaut, when he measured and it took 2 hours or whatever, the 3 hours, that is the proper time, T, according to him, because it was his clock. Therefore, you can now know it in terms of the relation with mission control, where mission control says, ooh, it took so long for the signal to come back from the astronaut here and there, the GPS. And so that is their mission control time, which you can relate by saying that this is the proper time, and it is the mission control time times the square root of 1 minus v squared. All right. So are we okay with this so far? These two, astronaut issue. Okay. All right. Thank you. Oh, so I do have an extra arrow here. I thought I did it for the other one, but here, this one, mission control says that it took so many hours. So this is what is the mission control, but the proper time is the one recorded by the astronaut himself clicking. All right, so now we are going to go with a problem that was actually already in the lecture notes. The astronomers have measured that Alpha Centauri galaxy is so far away that it would take light 4.37 years to reach it from Earth. But they want to call it light years. So they will then say it is 4.37 light years, meaning the distance, the actual distance, is light traveling at 3 times 10 to the 8 meters per second, and it took light 4.37 years. So the unit is now LY, light years, all right? And then they say, oh, there is an ambitious plan to send a spacecraft with speed v, but speed v again measured in units of the speed of light. So it may be like 0.9 times the speed of light, meaning that spacecraft really is zipping through the space at about 90% of the speed of light. For an observer on that spacecraft, namely for that astronaut how far did the spacecraft travel in order to reach Alpha Centauri? See the question here? How far? Because he will now say, gee, I just need to set my clock, right? I'm the Captain Kirk. I'm the Captain Kirk, right? Spaceship Enterprise. And now I start my clock and say, okay, it took me, let's say, I don't know, 2 years or 3 years or something. And so I measure my clock. But I also know that this Alpha Centauri seems to be rushing towards me. I'm on the spacecraft, and Captain Kirk will say, I didn't do anything. I didn't ask my Mr. Scott to turn on the rocket. I'm already going along at 0.9 times the speed of light. I am now going at constant speed. And what I see is this Alpha Centauri, oh, it's rushing to meet me. It is rushing to meet me with velocity of what was, whatever they told us is the speed, 0.9 times the speed of light, let's say. So it is Alpha Centauri that is zooming towards me. I'm not moving. I'm not moving. But now it is coming towards me, and I can now say it took a certain time for this Alpha Centauri to come to me. That time is the proper time, and the distance is now this velocity times this proper time is therefore the distance I would measure. You see what I'm saying here? This is now, how far did the spacecraft travel? According to the Captain Kirk, he says, we traveled using the fact, elementary physics, using the fact that Alpha Centauri is rushing towards me at 0.9 times the speed of light, and I have measured with my clock, my stopwatch, my very nice stopwatch, atomic clock, that it took, let's say, so many years, 2 years or 3 years. Therefore, the distance that I travel, or another way of saying it, distance that Alpha Centauri travel in order to meet me and to greet me as a good cousin or a good relative, is v times this proper time. So you can say what is involved is this thing called Lorentz contraction. And if you look up your notes, somewhere you find this formula. But now you again have to now say, which is the proper length, which is the distance that Captain Cook would measure. And here, this, you have to sort of, this is Cutnell and Johnson. They use this set of notation, but we have to get our concept straight. And now, first is this distance. This is the distance that the mission control says that it was very far away, 4.37 times the speed of light, very far away. But on the spacecraft, the astronaut will say, no, it was a short time. It was a short time. And the distance is actually, the distance is therefore the contracted distance. L is what was the ground observer times square root of 1 minus v squared over c squared. All right? Are you able to grasp this? Let me say it again. I am Captain Kirk. I am on the spaceship Enterprise. I am not accelerating. I happen to have, because Mr. Scott was able to boost me, or NASA was able to boost me, so that I am now going with 9.9 times the speed of light. So I am going. I am not accelerating. I am inertial reference frame. And what I see is Alpha Centauri is rushing towards to see me, to greet me, to meet me as long-lost cousin. And it is coming to me at velocity 0.9 times the speed of light. And I can therefore know how far did Alpha Centauri travel. Well, it is the speed v times my time that I have measured with my clock. So that is the distance that this question is asking for. What is this L? And this L is the contracted time length. This is called Lorentz contraction. And this other one is the distance as measured by the guy on the platform, like in the train station, or the guy measured by mission control. So this is what you use as L0, and this is the answer that you're looking for. It is the L0 times square root of 1 minus v squared over c squared. And in this notation, L0 is d. L0 is d. And again, because you have measured the speed in terms of units of speed of light, then v over c becomes just v. All right? Is this okay with you? Okay. So far, just one yes. Let's go for two yeses. All right. Thank you. Okay. All right. So now let's go on to 11. This is now looking at a different aspect. It's the same situation, but different aspect. This random block includes the question on the distance as measured by, yeah. The astronomers, yeah, we were going through the same issue. We know Alpha Centauri is 4.37 light years away. They call it the distance of 4.37 light years. There is an ambitious plan, but now, how many years did it take? And again, has to do with the guy on the spacecraft. These questions were hard. Well, no, that's why it's you have to sort of vaguely, oh, this nasty professor did cover it in the chapter whatever 27, 28. This was discussed there, and what you have to do now is to rush there and then know what the formula means to apply it to this situation here. So we already know this question must involve relativity, because you can say it is so many light years and so on. It must be relativity. And then the question is talking about the how many years did the, so it must involve, we couldn't see all the parts together. That's why it seemed confusing. Yeah, I know. The blackboard just, it involves relativity. So you go to chapter 28, and then you kind of say, gee, it somehow must involve time dilation, but also involve length contraction, because after all, it says there's a length involved and there's a time involved, right? And so it is not just time dilation by itself. This question is sneakier. This question is more involved, right? So we now say, okay, I got to now recall that there is length contraction, because we already sort of realized that. And the length contraction involved this formula, right? But now we got to be careful which is the length that is the proper length that is now contracted. It's the contracted length now. Well, D is the distance as measured by the guy on the platform. You remember in the, what was it, in the tunnel, the train being trapped in the tunnel? D here is L0 here is the distance as measured by the platform. This L is as measured by the astronaut who is in a moving frame. He is in a moving frame of reference. All right. And now this is the formula that says that because you're moving, what was 4.37 light years, or what was, 4.37 light years, is actually less. How much less? Is square root of 1 minus v squared over c squared. The actual length that you and the moving observer will see is shorter than what the guy on the platform, mission control or platform, will say. He will say, oh, it was 1,000 meters long, the train. But you on the train itself will say, what do you mean? The tunnel is not 1,000 meters, but shorter now, because I measure Alpha Centauri rushing towards me with velocity v, and I already learned or clocked it. I already clocked it to say that it took it a certain time, so many hours or so many years. Therefore, I know what is the distance that I measure on my spaceship. That is the Lorentz contraction formula. Okay, but now I got to do a little bit more. Why? Because this question did not ask what was the distance. It was asked in the previous question. But now this question is same situation, but a little bit more complex or more tricky or more you need to think. What is that you need to think? I'm on the spaceship, and I already know that the length is contracted, but you want to know how many years, based upon knowing what was the contraction, how many years? Well, elementary physics tells us the distance traveled by Alpha Centauri. The distance traveled by Alpha Centauri is its velocity times the time as I have measured it on my stopwatch. It is this. Do you follow what I'm doing down here? This length as observed, measured by Captain Kirk on this Enterprise, he will say that Alpha Centauri rushed to meet me, and it was rushing to me at velocity v, and I already clocked it to be so many years or so many hours, depending on the situation, and therefore the time is related to this distance that Alpha Centauri did in coming towards me by t is L over v. I mean, this is 203. All right. And therefore, I can now say this time is this equation divided by v. The time that they are talking about, how many years, the time that they are talking about is L over v. And L was d square root of 1 minus v squared. Do you follow where this equation comes from, these two? Okay. Did you follow where this calculated formula comes from, these two? All right. Any questions here? Of course, the fact that this is 1 minus v squared or something, what? But you say that again, you didn't realize it. What was it now, your comment? Don't be
Professor,
shy.
on the exam, we were just like, we didn't know like which was our reference, like,
Yeah,
reference
I know.
point. So I was confused with that. Like,
Yeah, yeah,
was it
I know, I know.
the spacecraft, the observer on the spacecraft, like, was he like, you know, I was
Yeah,
just
yeah.
confused with
No,
that.
no, I'm not I'm not saying you have no excuse that you should have known it better. No, no, I'm not saying all of that. I'm going through all this in order to help you to now say, gee, I kind of remember somewhere in one of the lectures involving special relativity that there was this. And now what you have to now sit back and now say, who is the observer? The observer is on the spacecraft, so it's in a moving frame. And then in the moving frame, oh, whatever time that you measure, that is the proper time. And then in the moving frame, the length of anything is whatever is the time times the velocity that this guy is, this spacecraft, this Alpha Centauri is coming to meet me. All right. So sort of begin to first learn or recognize, I should go immediately to chapter 28. That's good. But then also to dive into it and then say, I should use this formula. Good. But then how to use this formula? That's where you have to scratch your head a little, okay? I'm not saying it's yeah, I'm not saying it is so trivial. It's not. But that's where you need to sort of now, I have spent some extra time in order to help you begin to see how you can plunge into a question on the final. I'm not saying that the final will have this question, please. It is not. You cannot repeat the same question. But some aspect of it, some Different way of looking at it, I may ask. Yeah, similar, namely different way of asking. Maybe it's not Alpha Centauri, maybe it is, I don't know, Jupiter. Well, it's too close, but Jupiter or Neptune or something, okay? Yeah, it involves the same basic formulas. It's not that the formula is now more complicated, but it is how to use that formula. That's what I'm trying to show. It's the set of formulas, but which one is L0, which one is L, and what is V, and what's the time, it's mixing around, okay? Shall we go on now? Yeah, okay, let's go on. Okay, number 12. Oh, this one is involving lenses, and it's a good one in chapter, I think this one is chapter 26, yeah. An object of height h, so there's an object here, it's of height h, centimeters, just so long as we are consistent, is placed at a distance d, capital D, from a converging lens that has a focal length of f centimeters, as shown in the diagram, okay? Where is the image located as measured from the lens, and is the image real or virtual? All right? And then it gives you all these 1, 2, 3, 4 answers. And the comment here is, while you're tackling this problem, be prepared that this random block includes a calculation of the height of the image. Okay, just to prepare, all right? And so you immediately go and you say, sure, I know this is chapter 26. I go go to my lecture notes, and there is a picture here with the formulas. Okay, I mean this picture identifies what is the distance, object distance, that's d0, and then it identifies where, and if this is your focal length f, it identifies where the image is. That's called the image distance, called d sub I, image distance, and there is h sub I. h0 is your original object height, and then this is the image, h sub I, and the magnification is hi over h0, which is negative di over d0. That's by just the geometry. You take this geometry here, you know this geometry and that geometry, you can then figure out that this height is related to d image over d0, object, the image over the object, all right? So now here, it's clear. We already know this d is object, capital D is the object. So this would be 1 over d, and they want to know where is the image. Where's the image? Well, image is 1 over little d. All right. And so the image is little d. The object distance is capital D. And you already told f. Therefore, algebra, you work out the algebra, it's this. No, it is this. I mean, that's little algebra which you have to work on your own piece of paper. You put down 1 over capital D plus 1 over little d for the image equal to 1 over f, and therefore 1 over d is 1 over f minus 1 over capital D, and then this is therefore the algebra. But this algebra does not yet tell you whether the image is real and upright or real and inverted. But this formula tells you if indeed your object distance is d0 on this side of the lens, it's algebraically positive. And if your di is negative, when you work it out, your di is negative, then the image will now be over here. But if the di is positive, it is on that side. I mean, this is the lens formula, and there's an algebraic. You have to look up the lecture notes, and you will find that there is this algebra associated with this very famous and simple, elegant little formula. And if the result with whatever is your d and whatever is your f, if your di is now negative, it would mean that it is on the wrong side. No, yeah, it's in the wrong side of the lens, on this side. But if it is this side, then di is positive. But when you do this number down here, it depends on whether that number is positive or negative. And if your di is now positive, then the image is now inverted. All right, so that is the if you go back to your slide, you will see that rule about when something is positive, when something is negative. If you put an object in front of the lens to the left, then that is positive. And then if the image is on this side, then it is real and positive. But if the image distance is on this side, because of the fact that you have put it too close, then the image distance is now negative, and then you can then see that it becomes larger. And if di is negative, then the magnification is positive and it is larger, but upright. Here it is now real, but down if di is positive. So this is what this answer is. It is real and inverted. You have to look up your lecture notes. You'll find those algebraic rules on this. Okay. Now, this is to follow up on that, where you now want to know what is the height. You remember there's this height. This formula says that the height of the image is related to your distance of the image distance. And there is this minus sign, which says that if it is minus, it means it's inverted. If my di is indeed on this side of the lens, then di is positive, but now the hi is now minus, so it's therefore inverted. If the image is on this side, it's inverted. If the image is on this side, di is negative, then it is positive. So here you now say, well, the height therefore is the same formula. You can now figure out, because you're using, or did I reproduce it? I reproduce it here. So the height is di, the image distance over the object distance times the original height. Original height is h, and the algebra here gave f over d, capital D minus f. But now I did not stress it, so I told the grader to now give full credit if they gave a minus sign for the inverted image, because what I meant by this is, what is the magnitude of the height? I should have put this, what is the magnitude of the height? But since I didn't, for those of you who then use this formula and then got a negative, you will get full credit. I told the grader, that's where my highlight here is, to give a full credit if they gave a minus sign for the inverted image. All right. Okay, so now let us come to this one. The figure shows the path of a ray of light as it travels through an unknown liquid and crosses a boundary into air. So this is N1, this is N2, where it was coming from the liquid and going out. All right, and the angle of incidence is I have theta 1 and theta 2, where this is theta 1 and this is theta 2. What is v? The speed of light in this liquid. The speed of light in air is 3 times. Oh, I didn't do this. Well, I didn't do this. I didn't. Yeah. Okay. Well, now this clearly involves somebody's law, and you will say, "Yeah, I remember this chapter 26. The very first thing is this thing somebody called Snell, right? Snell's law. Yeah, you sort of remember. He's not smelly. He's only Snelly. Yes, he's a Snell's law. He's not a Smell's law. But anyway, forget about the joke. Snell's law, right? And Snell's law says whatever is n1 sine theta 1 is equal to n2 sine theta 2. The only thing I better be very careful is which one is n1, which one is n2. And since they say it is light that came from here, up there, therefore this is n1, that is n2. All right? You got to be, you say, I know, I just have to use Snell's law. I have to use Snell's law. I run to chapter 26 and I say, I use Snell's law, and boom, I reproduce this. But you got to be careful what you use for the N1, what do you call N1, what do you call N2. But now the other thing that you need to use is the speed of light in this. The speed of light in this liquid is the velocity, not the velocity, yeah, the original speed, velocity c, 3 times 10 to the 8, divided by the n of that medium. All right, and so you now say, well, I need to know which is the right formula. What happens is I have n1 sine theta equal n2 sine theta 2, but n1 is c over, is the velocity, velocity is c over n. So the velocity in speed in the liquid is v1 is equal to c over n1. You follow what we are doing? I should have. I guess I didn't. Oh, I didn't. So I should have. When I upload it, I will write down. You know what I'm talking about. Let me just quickly do this. Sometimes I'm able to do it. Sometimes I'm not able to do it. Let's see. Pen. Yes. And pen. Pointer observations. Arrow options visible. Oops. And what I need to say is velocity. Okay. Come on, I thought I did. I already put. Yeah. Pointer options visible and velocity. Okay. And velocity. Well, okay. Oh boy. Oh, now I can't even see the pen pointer observation. Well, you see what this is. Velocity in 1, because that's what they want to know. What's the velocity in this medium? Velocity in 1 is c over n1. And so what you need is to bring n1 over here and bring n2 over there. And then it becomes, this formula becomes here. Are you following what I'm doing here? I'm sorry, I should have put in. Are you following? Yeah, you understand what is involved. N1 is the index of refraction. Velocity 1 is equal to c over n1. So from here, you have to move this one over here, move that over there. Therefore, the velocity is c over n1, but 1 over n1 is sine theta 1 over n2 sine theta 2. So this is the formula. Okay. If I had to take the Blackboard exam using my slideshow here, I would be in a real sweat because I cannot even do the simple things like writing on it. It used to be that I could, but I don't know why ever since of the update, it's so difficult. Microsoft keeps updating the PowerPoint 365 and so on. I don't know. All right, any questions about this? It's really using this and then recognizing that the speed of light in this medium is c over n1. And then therefore you have to bring this and you have to bring that. Okay. All right, so now let's go on. Okay, so now this is a good thing for a real life situation, because when you travel, when the pandemic is over and then you travel and you're driving and you want to come to a motel somewhere, you know, after a long day's drive, and then it's hot, you want to, you know, get into the swimming pool and so on, be careful that if, let's say, your child or you were sitting at the edge of the swimming pool and you see a coin or your key or whatever is valuable that is resting on the bottom of the pool, the coin or this key or treasure, it appears to be at the so many feet directly below the water surface, right? A certain distance, feet below. How deep is the pool at that location? And be careful. It always appears to be less. The coin or the key or the treasure always appears to be less. And if you are fooled, you may then plunge into that pool thinking that you want to retrieve it, but the pool depth is actually longer than your height. And that's why all swimming pools in motels, in hotels, at night, they have to be lighted, and they have to have the words next to wherever the section is and say, this pool is 9 feet deep. Over here it is 10 feet deep. Over there it is 6 feet deep, and so on, because you get easily fooled, right? That's daily life experience. But now for this question, they say, since you saw this coin to be little d feet directly below, how deep is the pool at the location? The index of refraction of water is 1.33. Well, we again say, oh, it is Snell's law. We know it involves Snell's law. And then you quickly go to your lecture notes and you say, ooh, I remember that there was a problem or a discussion of this apparent depth thing, right? And then there's this formula that says, oh, I mean, this picture that shows that what was actually deeper, the actual depth, the apparent depth is much less. Okay? So you can say, gee, oh, I know now. And the only thing you have to be careful in trying to use it is to say, what is N1, what is N2? Well, N1, because the what you see is the light ray that comes from the bottom. So it is now, this one is N1, this one is N2. This is the light ray coming from water into the air, all right? And then you see in your lecture notes that, oh, there is this formula that says that the apparent depth is less than the actual depth by this ratio, where it is N2 over N1. The only thing you have to be careful when you rush to your lecture notes for chapter 26, and then you say, oh, I know, there was this figure that already discussed it, I can immediately copy it over here. But be careful, what is N1, what is N2, what is D, what is D prime? This picture says D is the actual depth, D prime is the apparent depth, whereas what you're given here is what is the apparent depth. You want to now know what is the actual depth. All right, so first you have to say, what is this index of refraction in this application of Snell's law, or in this application of this formula? You have to then say, oh, but this light ray came from this water up into me, therefore N1 should be here. So N1 is 1.33. N2 is 1 because that's air. All right. And then the other thing is, they are asking for how deep is the pool. Well, how deep is the pool? It's the actual depth. So it is now here. The actual depth is here. This is the apparent depth. So when you use this formula, be careful. Which one do you use for D or D prime, N1, N2? You got to sit back. You say, I already located this formula. Yes, you have located this formula. But how you use it, you have to now say, what is this question telling me? Or they told me that they know what is the apparent depth, which this notation here is D prime. So therefore, they have told me D prime. And now they have told me what is the index of refraction of the medium from which the light ray came. So that is N1, 1.33. N2 is 1. Therefore, the question they want is D. And now you can immediately do the algebra. D, the one that they want, is this, which is in this notation here, little d, times 1.33. And so therefore the answer is 1.33 times whatever this thing is in feet. All right? Have I exhausted you? No, not at all. Good. What I hope I have been able to teach you is, you first immediately say, I know what you're asking. It involves concepts in chapter 26 or chapter 27 or chapter 28. And then you rush to chapter 26, 27, 28. And then you have to now identify, oh, there's one formula which is somehow involved in here, but then you got to be very careful. What is D? What is D prime? What is L? What is L0? What is V? And so on. It is there that you get your extra credit. You can be dumb. You plunge right in and then you get the wrong answer. And I cannot help you. But if you now say, I now have found the, it's easy to go find to your lecture notes and say, here, it is this. But to now sit back and say, which does this apply? Which formula, which part of this formula apply to this, and which part of the formula applies to that? All right? Any questions? Can somebody read that? Yeah. Can
For
somebody
the
read that?
last two
Hi,
exams,
Professor.
What?
Uh, yeah, so I was just asking, for the last two exams, we were able to see like which questions we got wrong, like at least like zero, or if we get credit for the specific questions. But for this exam, like I wasn't able to see the questions after the first submission. And I was wondering if it's something you changed in the settings or it was just a glitch with the Blackboard.
Yeah, I don't know. I know there are some people that say that they could not. I don't know because Blackboard is so fussy that it even confuses whoever is giving the test. So I don't quite know how to answer. But somehow it didn't occur the previous test, right? I have to then go back
Yes,
to the
exactly.
previous test. Yeah, I have to go back to the previous test and then look over exactly what was the thing that I clicked, and then to see what did I click for this test 3, and then basically say, oh, I better not make that same mistake because final is much more important than test 2 or test 3 by itself. So
Yes,
I will
yes.
fix that. Yeah,
Yes, if
I'm
you could do that for the final, it would be really helpful. I really
yeah,
appreciate it.
I
Thank
know, I know. uh,
also, Professor, it would be
yeah,
great if you could, if you could give us more like variety of questions rather than focusing just on one question, like with, you know, one concept with the same three questions. So it's like hard for us. Like if we don't get one concept, we don't get all the three questions. So it would be better if we give like variety of concept questions. Did you get what I said?
no, you mean more multiple answer questions or more
No, like
multiple?
for the for the second exam, do you remember like we have like a F1 plus F2 like Y, Z or X axis. So we had to do like what's on the X axis or Y axis, something like that. So
Oh,
even for this one, like it was about the spacecraft, like
yeah,
spaceship.
yeah.
So it was like the same question. So it would be better for us if it's like variety of question rather than just like one. Yeah,
Oh, you're saying
I
that
don't know whether you get it or not.
I'm not sure I fully understand that. It may be that what you're saying is that for one random block, that the 3 steps in it were separately separated instead of as we had in one question, we had to combine 2 concepts together. What you're saying is that, like over here, uh, what was it? Yeah, like
Yeah,
this. It
Professor. Yeah,
involved
for
this and that, right?
yeah.
And so you
Yeah, so
say,
what I mean is like it involved like light year. So we were confused with the light year and a reference point, right? So we got like both of the length contraction as well as the time, like how much time it took. We got both the answers wrong because it was same question but just altered differently. Like only the question was changed a little bit. One was asking about the time and one was asking about the length. So it was basically the one question, right? So what I'm trying to say is like if you give us like a different like variety of questions, I think we will get because
yeah,
we
yeah.
were just
Well, I
confused
have.
with the light.
By the
Yeah.
way, to make a question easier is actually hard on this guy. I don't know if you understand what I'm saying. To make a question easier is actually harder. So, but I have to work on it. So I will try
Yeah,
to think
Professor,
of
I
some.
can understand like we just had few chapters, so it makes hard for you to make like variety of question. But for the finals, we have like a lot of chapters. So if you
Yeah,
could include like variety of like questions with variety of concept, it will be better. Because if we get stuck on one, we will get like other questions, right? Because we have
yeah, yeah,
studies,
yeah,
like we have prepared for something, so it would be better.
yeah, yeah. No,
But
no. For
just
the
a
final,
suggestion.
there will be yeah, there will be more variety because there are more chapters involved. And actually, we should not forget it's electric and magnetic, things that are most important. Special relativity, you say, oh, it is just to please Einstein, right? So I'm not going to hammer you and say, oh, how come you don't know what Einstein already taught us? But I would be very concerned if you do not know about electricity, about electric forces, magnetic forces, and about sound, because ultrasound is one of those important things that the biomedical profession needs, right? So the early chapters will be revisited in the final, although we will include some of the later parts on Einstein's relativity and wave particle duality, which are not exactly important for biomedical, but it is part of the course. So that's why I took one whole session now to go over test 3 in order to show you how you can actually now always begin to sit back and then have to actually know the algebra skill to help you to figure things out for what they want. But I will try to see how to make it less stressful. All right, is that a better way to say it? Okay, I think it's good enough. I'm already exhausted. We won't start on chapter 29 till next Monday. And the grader, it's up to the grader now, but I don't think he must be already traveling somewhere. So maybe he's going to Alpha Centauri, and I don't know if it will take him so many years to come back, but let's hope not. And we will see whether he will have it all graded by Monday, 5 o'clock. If not, it will be 3 o'clock. I mean, Wednesday. So just have a good Thanksgiving dinner. Yeah, you have a question? Oh, but you wait until everyone leaves. Have a good Thanksgiving time. The grader is not your TA. No, it cannot be. It has to be a different person. So have a good time. Relax and enjoy this time with your Thanksgiving, with your family, because it's only once a year you have this time together. All right. So be joyful, be relaxed, and one day you can be, biomedical profession and then help your family for whatever situations they may need involving ultrasound, and so on. Okay. So, all right. So have a good holiday and see you online next Monday.
Thank you,
Thank you,
Professor.
Professor.
Have a
Okay.
good
All right.
Thanksgiving.
Your
Happy
Yeah.
Thanksgiving.
Same to
Bye bye.
you. Same to you.
going through the exam was helpful. Thank you, Professor.
Yeah. Thank you.
Professor,
Yes.
quick question or a quick suggestion.
Right.
For if you go back to question 7 and question 8,
Oh, yeah.
the little side notes that you add, it says calculate. This is a multi-answer question. It says, I guess for some people, if you look, for example, at question 5, it says the next calculated question for dark fringe, but in the question they ask bright fringe. So just like for, I mean, I got this question right, but I guess there could be a misinterpretation because on the bottom of question 5, for example, it says this is part of a question on dark fringe, but the question is asking for bright fringe, so that's a slight
Yeah.
confusion. And that's not the only thing, but also uh, um, these I guess it's some of these questions I felt were a little bit difficult to like in wording, and
Yeah.
also for example the length and the time dilation question, they depend
Yeah.
on each other, and
Yeah.
I find one of the advantages or one of the disadvantages depending on who you are, if you get a random block question that gives you the formula first, you're in an advantage for the calculation part of of that same block question.
Yeah. I
Do you
know.
see what I'm saying?
I know, I know. I wish I can get that Blackboard, CEO, whoever is in charge of all this, to say within that random block, please don't randomize it. But our City College person involved with Blackboard has no authority.
I'm just giving you a heads up because those are
Yeah,
issues that are common with students. I mean,
I know,
I
I know.
noticed it even though I caught the mistake. But
Yeah,
yeah,
I know, I know.
thank you,
So,
Professor.
okay, all right.
Have a good holiday.
Same to you. Same to you. Oh, I better turn off stop the recording.